So my name is Joost Kuijer. I'm a medical physics expert working at the hospital here at the Radiology Nuclear Medicine Department. And sort of my expertise lies in MR imaging. And this week, basically the theme will be neuroimaging. So I talk about MRI in general, but the focus will be on the brain. And we also chose to put some more emphasis on diffusion-weighted brain imaging. So we have a practical about that and also some lectures. So first lecture, it's about relaxation and contrast. So that's the basic topics we're going to focus on the next 2 hours or something. There's a lot to tell about it in very much detail, and I have to choose some kind of level of detail which I'm going to explain you. So to limit the kind of technical depth we're going into, there's going to be some open ends. So I also do this lecture for the medical natural sciences, and there we really dive into the depth, and there we really explain to a very detailed level. But because you're a little bit less technical audience, I probably have to sort of warn you that there's going to be some open ends, and I just explain you like, okay, this you have to sort of accept the way it is. But we'll see where we end up. We start off with the CT image, and I take it as an example because relatively compared to MRI, the CT is kind of easy to interpret because the contrast is always kind of the same. So a brain on a CT images, they mostly look like this. So they have a skull, which is very bright, and then you have the softer tissue, which is a bit grayish, and it always looked like this. So you can change the window level setting, how the image is presented on your screen, but it doesn't really change the content. So the unit that is on the screen for a CT image is the Hounsfield unit, and it's always like that. And the Hounsfield unit, does anyone know what it sort of represents? Hounsfield unit. What is depicted on the CT image? Sorry, the absorption coefficient of what kind of stuff is absorbed? Yeah, so it's basically the photons of the X-ray. So you have the absorption, and you could also say like the image represents the attenuation of the X-ray, and it's always like that. So the brain has a kind of always the same kind of contrast. There's a similar story for PET, and with PET you inject a radioactive tracer, and it travels through the body and it accumulates at some point where the tracer is absorbed by the tissue or whatever. And basically the PET machine depicts where the tracer goes, and it shows you that on the images. So it just shows you the absorption of the tracer. And it's always like that. With the ultrasound, similar story. It always represents reflections of the ultrasound. It's always like that. Then we have the MR image, which is a bit of in contrast to the other modalities. Has very different kind of phases. So the MR image doesn't exist because there's a lot of knobs and settings on the scanner itself that allow you to change the contrast. So the appearance of the images is very different, and also functionally what you see in the image is also highly dependent on the settings. So that makes MR imaging very complex. It also makes the interpretation of the images a bit more complex. But yeah, a kind of unlimited number of variations is possible, but it's also sort of the power of MRI and why it's very, very much used for imaging of soft tissue. Now, there's also a lot of jargon associated with MRI, which makes it a bit more difficult if you are not really familiar with MRI. You read a paper, you think something, oh, I would like to know some more about that. It's a bit difficult to read the paper sometimes because there is a lot of jargon in there, and also a lot of short names like MP-RAGE. They talk about bold, T2 star, proton density, T1, T2, FLAIR. So, you know, if you don't know what that means, it's really makes it difficult to read the literature. And the other thing is I can't explain all this in detail. It's just too much. So that's why we decided in this lecture to focus on the basics and also explain a bit how it works, which mean if you know a bit of the theory and the principles, it's easier for you to extend the knowledge to other variation of the same idea. So the very basic is proton density, I think. So here you have a proton density image. There's my pointer. This is proton density weighted image, and the proton density is always there in every image because protons are the basic unit that gives the signal. I'll explain that later. And if there's no protons, you don't get signal. So that's kind of easy. Then you have something that's called T1 weighting. That's my pointer. T1 weighting here on the left side of the slide. And basically the proton density is always there also if you have a T1 weighted image. But most people forget about that. So the proton density, I'm not going to talk a lot about that anymore because it is there in every image, but it's not the most interesting contrast, and it's dominated in this case by the T1 weighted contrast. Then on the other side we have, well, surprise, surprise, T2 weighting. So there we have, and you see that all three images look different. So you have to know what kind of image you're looking at to interpret as well. Now there's two important knobs on the MRI scanner, and you can set those if you start making a scan. And the one on the left-hand side is called repetition time. Again, I'll talk about a bit more about that later. But for now, you have to remember that if I rotate that knob, it's like mixing in that signal. It's like DJing. I mix in that signal, and the more I dial the knob, the more I mix in the T1 weighted contrast. There's another knob on the other side here. There it is, and that's called echo time. So it's a different knob, and again I can mix with that knob in the T2 weighted contrast. So far, pretty simple, I'd say. And then what are those T1 and T2? Those are actually tissue properties. So here's a list of different kinds of tissue classes, and apparently they have different T1 and T2 times. And then here's an example. So on the right-hand side, you see a T2 weighted image here, and you see that the CSF, the spinal fluid, is very bright. And so apparently some tissue with a very long T2 has a bright appearance on T2 weighted images. I'm going to explain that later, but for now you just can remember it. And then here we see the gray matter, which has a way shorter T2 number, and then apparently that's kind of dark gray. Now then, also I have a T1 weighted image, which is now a different organ. Here you see the heart. So basically here in gray you see the muscle of the heart, and then dark here on the inside is the ventricle. And then we're gonna look at the T1 times now because it's T1 weighted. And apparently if you have a bit of a longer T1, it's kind of darkish gray, and then fat, for example, has a very short T1, and apparently that is bright on T1 weighted images. So the contrast, we now already learn, the contrast is kind of opposite of the T1 and the T2 weighted image. So a long T2 is bright on T2 weighted images, and a long T1 is apparently darker on T1 weighted images. Okay, so I'll explain later how that works. So for now, we should remember that the most important choices are repetition time, echo time, and here you see the different contrasts again. So T1 on the left-hand side, now with the choice of repetition time and echo time, proton density weighted and T2 weighted. And they all have different settings of the echo time and repetition time. Okay, so here's kind of overview what we're going to talk about. And what is kind of important, and I learned that from the past, that it might be rather confusing talking about repetition time and the contrast. So you have to remember for yourself and make sure that you understand that there's a source of contrast, which is basically the tissue properties, proton density, T1, T2, T star. So those are tissue properties. And then on the other hand, I have a choice with the dials and knob on my MRI scanner, which of those properties I make dominant in my MR image. So I can choose to make a T1 weighted image. So, and that is determined by the settings of repetition time and echo time, and those are settings on my machine. But the T1 itself, again, is a tissue property. So I have a choice of these, what they call scan parameters, repetition time. I can also choose the field strength, 1.5 Tesla, 3 Tesla. There's a lot more other settings I can do. And for example, I can also choose to have a different kind of sequences, and I will also talk about that. So I can use gradient echo versus spin echo. And they also determine the type of contrast. And then there's a last thing I would like to mention here. I'm also going to explain something how contrast agents work with MRI, because again, that's a bit different from CT. So, on what actually is signal? What is the gray value? What does it mean on MR images? So, on CT we know that we talk about attenuation or absorption of X-rays. But for MR we do not really know. And where does it come from? What's the origin of the signal in MR images? So let's have a short look at that. And at some point I found this recipe on the internet, and the source is on the bottom of the page. So I sort of modified the slide a bit, but I copied the images from there. And then now let's have a look at the field strength. So apparently we need a very strong magnetic field. And 1.5 Tesla is a typical field strength of a scanner in the hospital, and then that is about 30,000 times the strength of the Earth magnetic field, so it's pretty strong. And the reason why we need such strong magnetic field is that we actually have the spins, the protons that are abundantly present in our body, because we have a lot of water and there you have a lot of hydrogen nuclei. And without a magnetic field, they have a random orientation. But apparently they are a bit similar to compass needles. So if I apply a strong magnetic field, then the compass needles, so the protons, will align with the magnetic field. And we need that to produce that MRI signal. Now, the alignment turns out to be rather weak. And that's a quantum mechanics effect, so I'm not going to explain it. But you know, there's a lot of energy sort of at atomic level. So there is a lot of sort of chaos, sort of to say. And I try to limit that chaos by applying the very strong magnetic field. But the reason why I need such a strong field is because the alignment is only very weak. So the compass needles effectively do align, but if I have 10 to the 5th of the protons, then only one will have a netto alignment. The other ones will have opposite alignment because there's a lot of energy, so they jump back and forth between the energy states, and only one will have that net alignment and produce the MR signal we're interested in. Now, fortunately, we have a lot of protons in our body because we have a lot of water. And that's also the reason why water is a good thing to use for the MR imaging, because you can also do the MR imaging with carbon or fluor. There's a less of those atoms in our body. So you have a very weak signal there. Now, and then we're going to have a closer look at the compass needles. So they do align a little bit, but they also start rotating. So they rotate like the Earth, but they also make this sort of precessional motion. So the rotation of the protons is around their own axis, but the axis of rotation also shows this precessional motions as shown on the animation there. And the precessional motion is key for MR imaging. Let's have a look at that. Now, my recipe continues. It's not too difficult. We're on step 2 of, I think we're doing 5 steps in total. Now we need to disturb the system because we're not getting signal. We just have the alignment of the protons. And to disturb the system, we are going to apply radio waves. And when you apply radio waves at the appropriate frequency, you can change the orientation of the spins of the protons or the compass needles, whatever you call them. So here I have this sort of sketch of the MRI scanner. The main magnetic field of the scanner itself, the 1.5 Tesla strong magnetic field, is horizontal. It's the big arrows. It's denoted with B0 there. And here I have a couple of those spins that are aligned with the field. Now, if I apply radio waves, there we go. So I put a lot of energy into the system, and then the spins rotate. And in this case, they rotate 90 degrees. So they are not aligned with the field anymore. They are rotated orthogonal to the field. That's the result of me putting energy in the form of radio waves. And to interact with the protons, with the compass needles, the radio waves need to have a certain frequency, which is called the resonance frequency. And that frequency is exactly equal to the frequency of the precessional motion. So that's a key thing. So it's called the Larmor frequency also, or the resonance frequency. And so the gamma is a nature constant. You can look that up in a book. We're not going to learn that. But what is important to remember is that the resonance frequency itself, denoted by omega, is linear with the field strength. So if I make the field stronger, precessional motion will also go stronger. If I make the field twice as strong, precessional motion will be twice as high. So for 1.5 Tesla, the Larmor frequency is about 63 megahertz. And if I increase the field strength to 3 Tesla, double it, then the resonance frequency will also double. It will be around 128 megahertz. And only with exactly that frequency there is interaction. If it doesn't match, there's no interactions, and the spins will not respond to the radio frequency. They will just ignore it. Okay, so what happens next? We did the excitation, we rotated the spins, and then after we turn off the radio waves, oh, by the way, the excitation is usually very fast. So you do like 5 milliseconds or even shorter RF excitation pulse. Goes super fast. And then we stop the RF wave, we stop putting energy into the system, and then immediately afterwards we're going to listen. We're going to listen to what the spins have to say. And they are going to emit energy again, and the energy comes out in the shape of radio waves. So they emit exactly the same radio waves we put in. And they also have exactly that same resonance frequency. So the emission of the radio waves we are going to receive with our coils and make the MR images from have exactly the same frequency, again the Larmor frequency. And they emit the energy and then they return to equilibrium state, which is aligned with the main magnetic field. Any questions so far? No. Okay, and then obviously we're going to receive that signal with an antenna, very sensitive antenna. The energy we put in and the sort of the power of the radio wave that we do the excitation with is way stronger than the signal that comes out of the body. That's a very weak signal, so we have to listen very carefully after we blast all the energy in. You have a question? Yeah. So the question is if it's only the one proton that's aligned with the field that sort of produces a signal and absorbs the energy. Yeah, it's kind of difficult to explain exactly because it's a quantum mechanics effect. So what we basically use here is a full bunch of protons and sort of describe how they behave. And they behave as if there is like 1 in 10 to the fifth of the protons that responds to the energy. But in reality, they do different kind of things. So they have interactions and they have different energy levels, etc. But yeah, sort of for now, you can look at all those protons as one group, and we put the energy into all the spins together, all the protons, and also the signal we are receiving is from the whole group. And we sort of really take care not to look at the individual spins because that is going to be very complex if we really try to understand. All right. So I'll leave the recipe for. Oh, you have another question? Yeah. So what I'm going to talk now about is the contrast, how sort of the main knobs, the echo time, the repetition time influence the signal and how you produce the different contrasts with that, the T1, T2 weighted images. That will be on my next slides. There might also be some other open end in your brain now, like, okay, we receive that signal with the antenna, but how do you make an image from that? And that's basically the step 4 and 5. So how do we know where the signal comes from in the brain? Because you know, well, the RF waves, this RF signal comes out of the brain into our antenna, but it doesn't tell us anything. Well, yeah, the signal comes from the brain, but not exactly where. So we can't make an image from that as it is now. But I will explain that on my lecture on Wednesday. So for now, we're going to look at the contrast. And I do that because we also have the practical tomorrow morning. And there we are again, you are going to play with the virtual MRI scanner and you are going to, you know, play with the settings of repetition time, echo time, and produce the things I'm going to explain now. You're going to play with that yourself. So we're going to look basically at the process after I did the excitation. I said like, okay, the spins are going to relax, return to their equilibrium state. That's where the magic happens. So I'm going to look at that process, that mechanism of relaxation, and it separate from how exactly the signal is there and how I make an image. So we're going to look why the one pixel is darker or brighter than the other. And we use transverse magnetization. So that is sort of the rotated signal with the 90-degree excitation pulse, and see what happens there. So this is a schematic representation, which I would like you to understand, because we're going to use that a lot in the next couple of slides. So it's a bit different from the one I showed before. Here I have sort of the man lying horizontally in the MRI scanner, and in this picture here below, the main magnetic field is in the horizontal direction. So the protons align with the main magnetic field. Now in the next couple of slides, it's more practical to have this main magnetic field vertically. So I sort of put my MRI scanner on the side, and the protons now align with the main magnetic field vertically, and I call that sort of the net alignment of all those massive amounts of spins. I call that M0, which is the equilibrium state of all spins together. And it's a vector, so it has a direction, it's aligned with the main magnetic field, and it has a length, which basically is the strength of the strength of the alignment. So that is the magnetization vector M. Then I do the excitation and they will rotate. And then in the schematic presentation, after the 90 degrees excitation pulse, so the magnetization vector rotates and it goes to the transverse plane. So this is what I call transverse magnetization. And I denote it by MXY because it's in the plane of the X and Y axis. And the longitudinal magnetization, so this component, the alignment with the field, is also called MZ. So why is that differentiation important? Well, so during the 90 degrees excitation pulse, the magnetization rotates to the transverse plane. It goes like rotation, like that. And then after the 90 degrees, right after the 90 degrees excitation pulse, the magnetization returns to the equilibrium magnetization, and then that happens while that is in process, two simultaneous processes happening, and those we will look at independently because they are sort of independent processes. There is the relaxation of a longitudinal component, so the MZ goes back to M0. It means if I rotate that arrow, my longitudinal component is 0 and it goes back to the equilibrium state. And then we have the transverse component, XY, it goes back to 0, and that is called spin-spin transverse or T2 relaxation. And the longitudinal component is also spin lattice longitudinal or T1 relaxation. So those names listed here are actually 3 different names for exactly the same process. They mean exactly the same. So you could also use them interchangeably. Okay, so there we go. We're going to look at those 2 processes in detail now. And the most difficult one we take first. The T1 relaxation. If we got that, the other stuff will be kind of easy peasy. So right after I do the 90 degrees excitation pulse, I explained that the magnetization vector is sort of rotated and then it's in the horizontal plane, in the XY plane. And I also explained it's a vector, so we can look at the different components. Now, if it's a horizontal vector, then the vertical component is actually 0 because the vector is horizontal, so there's no vertical component. So that's what I explained here. I tried to schematically draw on this first slide of the part of the animation. The sort of the arrow, the length of the arrow pointing vertically is 0 because the total vector is in the xy plane. And we're going to look at that vertical, that MZ component separately now. And then we see it grows back to the equilibrium state. So the vertical component grows back there, back to M0. And then the growth is actually exponential, and it has a time constant which is called T1. Now, and it happens because the protons, they exchange energy with the environment. So during the RF excitation, I sort of load them with energy, they absorb the energy, and during the relaxation process, they sort of interchange that energy back again with the environment. And the environment is the molecules that are around the water. And then the amount of coupling between the protons and the sort of the environment determines the relaxation speed. So it is a tissue property because the speed of relaxation, the amount of energy that is exchanged at what speed, is determined by the chemical environment. And then again, you see this is a list of the T1 values of biological tissue, and then the CSF, for example, has a very slow relaxation, T1 relaxation, and fat is very fast. And then again, so that gives us a bit of feeling of what happens, but it doesn't explain why fat is bright and the heart is dark. So I'm going to have a look at that. And here I'm drawing a so-called T1 relaxation curve. And vertically we have the magnetization, so basically how much of the vector is along that aligned with the field. And here horizontally I have the time. And I very conveniently sort of divided by T1 of tissue, so it's a very universal kind of relaxation curve, because no matter whatever the T1 of the tissue is, it always goes like this, because you divide basically the scale of the axis by the T1 of the tissue. And then here again you see like the relaxation goes exponential, and there's the magical T1 value of the tissue property, which determines how fast the curve goes back to equilibrium state. And in this case, the equilibrium state is aligned with the field, so they all the curves go back to 1, because 1 means that the z component of the relaxation is equal to m0, which is the equilibrium state. So basically what you have to remember is that all the tissues sort of go from 0 right after the excitation pulse. The longitudinal component is 0 because it's horizontal, and it grows back to the equilibrium state, and the speed is determined by the tissue property T1. Okay, so that tells us something about the relaxation process, but it still doesn't tell us why one tissue is darker or brighter than the other. And then, if we're talking about darker or brighter pixels, we're talking about contrast. And by contrast, I basically mean sort of a signal difference between the different tissues, different kind of gray values. Okay, so I have the same, where's my pointer? Yeah, so I have the same curve here, but now I've drawn it for gray matter in blue and in white matter in green. And the white matter has a shorter T1, so the relaxation of that curve goes a bit faster than for the blue one. And here now I have sort of a real time scale in milliseconds. And then sort of the contrast is the difference between the two tissues And if I look at the difference between the two curves, what I do see is that in the beginning of the curve, right after the excitation pulse, the curves are very close to each other. So there's not much difference in signal yet, right after the excitation pulse. If I wait a bit longer, the curves start to split up because the one goes faster than the other one. And then if I wait still even longer, they go back close together because both will end up after a very long time, they will both end up at the equilibrium state. So again, if I wait long enough, there is no signal difference. So this is the curve that sort of draws the signal difference as a function of time between the gray matter and the white matter. And I see there's a kind of optimum in signal difference if I'm interested to get signal difference between gray matter and white matter. And the moment in time that this happens, the maximum difference between the curves happens to be roughly the same time point as the T1 value of the tissues. So here it's a kind of rule of thumb. So here I have the time point of interest is somewhere in between 600 and 950 milliseconds. So let's say 700, 750. That is the moment in the curve where they split up most, where I get most signal difference or most contrast between the two tissues. All right, so that's a rule of thumb. Now there is an issue because this talks about longitudinal relaxation, so signal recovering the spins, the protons aligning with the field, or the compass needles aligning back with the field after I disturb them with the RF excitation. But the oh, where's my pointer? Oops, there it is. So the contrast is in the longitudinal magnetization, but only the transverse magnetization I can measure with my antenna. So I have a difference in length of those factors along the longitudinal magnetization axis, but the signal I can only measure there. So we need another trick, which is another excitation pulse. Because what happens now, I have these two factors with different lengths, and they're not in equilibrium state. They would be if I wait long enough, but I sort of don't give them time to go back to equilibrium state because I'm interested to get that signal difference between the two vectors. And to measure that, I give another 90 degrees excitation pulse. So I rotate these factors back into the transverse plane, and then if I listen carefully to that signal, I will hear a signal difference between the signal coming from gray matter and from white matter tissue, which is depicted here by the length of the vector in the transverse plane. So this is actually a signal I can measure. This is the signal in the transverse plane, the rotation in the transverse plane, which is detectable. And the longitudinal magnetization I cannot detect. It is there, I cannot measure it. Okay, so that's a pretty complex process because I actually need two 90 degrees excitation pulses to get a signal difference representing the difference in T1 relaxation speed of the two tissues. Let's see how we can use that in a practical way. So we need a repeated excitation. And let's start off having a look what happens in time. This is my first 90 degrees excitation pulse. The protons start off in equilibrium state, and then I do the excitation at time point 0 here. This is where my first 90 degrees excitation pulse happens on that axis. And then my magnetization factor goes into the transverse plane, and my longitudinal magnetization grows back to the equilibrium state. So that's there. This is the curve we saw before. The two curves, gray matter and white matter. And then here, this is the point in time where we say like, okay, here comes the next 90 degrees excitation pulse. Let's put it there. And then we saw we have these sort of vectors that have grown on the longitudinal axis, but we can't measure them. And by means of that excitation pulse, we rotate them into the transverse plane. We make them detectable with our antenna. So there we go. We have a signal in the transverse plane there, which is detectable, and the longitudinal magnetization goes back to 0 because we rotated them in the transverse plane. So what happens next? Well, history repeats itself. There we go. If after the excitation pulse, the longitudinal relaxation always wants to go back to equilibrium state. And it does that with the relaxation speed T1, which is again the tissue property. So we're back into the same state now. And we can do yet another 90 degrees excitation pulse. We get another longitudinal difference, longitudinal magnetization difference, which we put into the transverse plane. And then this happens over and over again. Now here comes the definition of the knob we were talking about previously, which is the repetition time. And it means here we have the time delay between the repeated RF excitation pulses. That is actually the definition of the repetition time TR. You have a question? So right after the 90, so the question is if the magnetization goes back to equilibrium instantly, right? So right after the excitation pulse, we rotate, during the excitation pulse, we rotate the magnetization into the transverse plane, and the longitudinal magnetization grows at the speed T1, which is the tissue property, which is the curve there. And the transverse magnetization also has a decay curve, which is actually T2. But I didn't talk about T2 yet. So that is why sort of the bottom half of this slide isn't properly filled yet. And it's just kind of, well, showing that there is a transverse magnetization. It is different for the two different tissues there. And what I sort of didn't explain, but you would have to accept as a fact, is that my antenna gets a signal which is proportional to the length of that factor in the transverse magnetization. So I have a signal, a detectable signal difference between the gray matter and the white matter there. Is that sort of answering your question? Can I have what different? Um, so I'm sorry, I'm not understanding your question. You mean in the transverse and in the longitudinal? Yeah, well actually, they do. So in reality, so the question is if the transverse and in the longitudinal magnetization exist both at the same time, and if they can sort of grow at the same time, and what happens to the factor. So in reality, they do both exist, and both T1 and T2 relaxation happen simultaneously, but they are sort of relatively independent processes. And the net vector, the sort of the real magnetization vector, would be the vector add up of both longitudinal and transverse plane vectors. But to understand it and to think about it, it's really useful to split them up because the net vector doesn't have a meaning. It is just that we think of the T1 and the T2 relaxation and the detectable signal in the transverse plane, which makes it kind of really useful to think about. So we always split up the two components, but in reality, what the spins would sort of experience is the net add up of those two components, obviously. Yeah. Yeah. The other way around. So the trick is that we actually need this sort of repeated excitation concept because the longitudinal magnetization is not measurable, but we would like to see in our MR image something which is T1 weighted, sort of a T1 weighted image, something that shows us, depicts us the difference between the tissues of the relaxation of the longitudinal relaxation speed. So the gray matter and the white matter have different longitudinal relaxation speed, which is called T1, which is a tissue property, and it's informative to us. And we would like to see that in the MR image. But the speed, the relaxation goes along the longitudinal axis, so it grows. It's the sort of the vector growing back to equilibrium along how good they align, the compass needles, how good they align with the field. But we can't actually measure that. We can't detect it with an antenna or anything. So what we need to do is apply the radio wave, do the excitation, have the spins sort of grow back towards their equilibrium state. But during that process, we're going to interrupt it at the time point where they didn't fully go back to their equilibrium state, because then, you know, we can't see any difference in relaxation speeds because they're all gone back to equilibrium state. So while that is happening, we can actually detect the signal change by doing another 90 degrees excitation pulse. And then we rotate that difference in longitudinal magnetization in the transverse plane. And that actually, the signal in the transverse plane is something we can detect, that we detect with our antenna. Yeah, yeah. So if I go back a couple of slides to the recipe, so this here on the right hand side, this signal that comes out of the body, that is actually only the transverse magnetization. And that dies out because the transverse magnetization also dies out, which is the T2 relaxation we're going to talk about in a minute. So we need to convert the sort of the longitudinal magnetization into transverse. And the only way to do that, as shown on this slide, is by doing that 90 degrees excitation pulse, and then it's in the transverse plane, and we can measure it. And then we're going to repeat that, and the repetition time, TR, is the sort of repeat, the time between the RF excitations. And it actually turns out to be useful for some reason, because to create the full image, we need actually to repetitively sample the signal, measure the signal. And I'm going to tell you a little bit more about that on Wednesday in the lecture there. But it does have a useful purpose to repeat the signal, and measure that signal over and over again to build up that MR image. And it's also the reason why the MR scans take rather long. So a typical MR scan would take about, a couple of minutes, maybe 5 minutes to scan the full brain. You need about 5 minutes on a modern MRI scanner. And that's also because you repeatedly do the excitation pulses and you repeatedly measure that signal to build up the MR image. So we have this little plot with the longitudinal magnetization there and the time after the excitation pulse there. And with the repeated excitation pulse, we can make this thing a bit more useful because now we have on the vertical axis the transverse magnetization, which is something we can measure as a function of repetition time. So this is a knob on the scanner. And it also shows that there is a kind of an optimum in the setting of the repetition time. If we make the repetition time too short, we're on this sort of on the left side of the curve here. We don't get signal difference between the gray matter, white matter. Actually, we don't get much signal at all because it's rather sort of on the low end. If we wait really long, if we have a very long repetition time, both curves have gone recovered all the way to equilibrium state. We don't get signal difference between the gray matter and white matter either. Actually, what would this be useful at all to wait this long? But what is the contrast? If we're not getting T1 contrast, what is the contrast that we're getting? Does anyone know? If you think of that very, very first basic slide. Proton density, yeah. So it's always there. And here I normalize the curves to the equilibrium state, but in practice, there is a tiny bit of signal difference, so a tiny bit of difference in equilibrium state between white matter, gray matter, which is the proton density. But it's not so strong. So if I actually sort of dial in the T1 contrast by shortening the repetition time towards this kind of part of the scale, which is sort of where the repetition time roughly equals the T1 of the tissue. That's a kind of a rule of thumb. Then we have that maximum signal difference and we get the maximum T1 weighting. So there we have it, the signal difference between the two tissues. And there we have, if we wait long enough, we don't get the T1 weighting, but we do get the proton density weighted image. Okay, so here's another example of the contrast changing with the repetition time, while the echo time, the other parameter, is constant. So you see that the contrast is kind of between gray matter and white matter is kind of optimal in this middle image, where the repetition time is roughly equal to the T1 of the tissues. Okay.
The good news is that the T2 relaxation is a bit easier to understand. The most complex one is the T1. This process of T2 relaxation will look at the relaxation of the transverse component back to equilibrium state again. And the equilibrium state, the transverse component is 0 because we only have equilibrium state. We have the compass needles aligned with the field. And there is no transverse component. So, T2 relaxation is called spin-spin relaxation or transverse relaxation. And it's the same as T2 relaxation. And the time constant of this process is obviously T2, and T2 happens to be always shorter than T1. Well, that is because of the underlying physics, also say, and the principles often really explain. But you will notice in this kind of tables that T2 of some kind of tissue is always equal or shorter. yeah, it has a kind of a similar source. So the two relaxation modes are somewhat related. But we are going to look at sort of independent. Now, I've shown this picture before early on in this lecture, and for example, the T2 of CSR is about 2 seconds, and it happens as you can hear that the pizza produces a bright signal on a T2 like this. In the gray matter, and a way shorter T2 relaxation path. Smart pass very at the darker on the T2. So we're gonna have a look and explain also see how that gets explained by the relaxation process itself. So we have a similar plot here. At the time point 0, we have the 90 degrees excitation pulse. And then right after, spins are going to go back to equilibrium state. So right after the excitation pulse, the transverse component is high because it started off before the excitation with a longitudinal excitation factor. The excitation pulse rotates it 90 degrees, puts it into the transverse plane, and that makes me have any long big transverse plane is like on this plot, and that is out towards 0, which is 100%. Again, this process is having exponential time constant. Now I need to define the echo time, which is the other sort of knob or the knob on my head to the right here. I have previously defined the repetition time, which is the waiting time between two RF excitation pulses. And then after I do the excitation pulse, I can wait a little time, which is called the echo time. The echo time is the time after the activity. So we could do those and won't I pick up the signal with my hand. Don't have to do it as fast as possible. I can deliberately wait a little. The reason to wait a little again is contrast. I would like to see differences in signal between the different tissues. If I look at the signal of the different tissues right after the excitation pulse, they all have a maximum signal, and there is no signal difference. If I do wait a little, and some of the curves go down faster than others because of the differences in T2 decay. So I choose my echo time to deliberately wait for the curves of the T2 decay to split up. That splitting up happens, well, roughly same order of magnitude as the T2 time constants of each of the cell. If I, in this case, wait for about 90, 100 milliseconds, again on the right hand side here, I have the difference between the signal of the white matter and the gray matter, and I get a maximum difference at around 20 seconds. But if I choose my repetition time, that knob on my MRI scan to be about 90 milliseconds, I sort of expect to get maximum signal between a white matter. And signal goes down, which sort of intuitively would not be a good idea to get less signal, get more noise, less signal, but the contrast increased. So if I want to see a difference between gray matter, white matter, I do have to wait for the curves to split up. So also, if you are going to tomorrow in the practical, the computer practical, I will ask you to produce a T2 weighted image, and this sort of echo time would be sort of a good starting point to get that signal difference between the two tissues. That also happens on real scanners, which is part of my job. If we get a new scanner, I have to sort of tune all the settings of the MRI scanner. Because it manufacturer the scanner with default protocols. So they were pretty okay. We should get rather nice T2 edit images. But the radiologists always have a sort of local, they have a local preference, what they were taught, and also depending on the different tissue types we're looking at, or the different disease types, you might want to optimize the MR scanner settings. All right. So to turn this graph into something practical is not so difficult because we just replace the wait time of the excitation pulse with my echo time, which is actually the definition of echo time. That's rather simple. And then here you have an example of a spin echo sequence. Repetition times now he fixed. I have changes in the echo time. And then here, and you see I choose the echo time roughly in the same order of magnitude as the gray matter and white matter, T3 excessive base. And you roughly get a nice contrast between gray matter. So we can also go back to this sort of complex graph, which I showed you earlier. The T1 relaxation is on the top half that we already discussed. Now we can also share the details of the bottom half, which is the T2 decay. So right after the exposure, here, second, and station, we have the transverse, the longitudinal navigation into the first plane. We have a different starting point in this gray matter and the white matter, but we take the length of this vector, longitudinal one, we rotate it, and starting for you. We also see another weird phenomenon because we see curve crossing here. It's kind of strange because we thought like, okay, if we want this sort of plus we need to wait a bit longer. So that is because we now have a situation in this graph where we have both mixed in T1 contrast and T2 contrast. Look at and from the first slide you already saw that the contrast on T1 weighted image and T2 weighted image is a bit inverse. So it's bright on the one, is dark on the other one. So if we mix in both contrasts, they tend to sort of cancel each other. And that's nicely by the crossing curves, because there we have no signal difference between the gray matter and white matter. So we have to basically choose either we have the T1 conference next in, which is shown here by the shorter repetition time. And if we want a really nice T2 contrast, we choose a different repetition time. What repetition time would that be? We don't want the T1 contrast, but we want T2 contrast. Now both options are sort of viable in that sense, but we get a lot of signal. Now, because then the curve is really low, so we give an excitation pulse. We have a very tiny bit of longitudinal limited signal recovery, and then we give another excitation pulse. And then we rotate a tiny little recovered longitudinal, let's say we rotate it in transverse plane, and we only get really tiny bit of transverse magnetization, which means very tiny bit of signal. So if we don't want the one contrast, we have to wait for both curves to recover all the way to a pretty long repetition time. Both the top half and the bottom half, they interact. Who is this guy where I do the That is the point in time where I transfer my signal from top to half. I can measure this signal, and the top half probably starts from the kind of reset because it always starts recovering from zero in case of an. And here I choose my echo time, and that means I can choose at which point in time and sample I measure this curve. If we don't want the T2 contrast, what echo time should we choose? Should we choose a very long or a very short echo time? Okay. Long one. So we wait for the signal to go down all the way down the curve. Where we get a sort of optimal signal for a T2 contrast. You don't want to, so you don't get the T2 contrast, but do we get any signal at all? No, because if we wait very long, then the sort of the signal that comes out of body, so remember the sort of the sketch where you had this body in the MRI scanner, RF signal come out that, and it dies out. So the longer we wait after the RF pulse, signal dies out, which is depicted by the curve down there. If we wait very long, all the signal is gone. We don't get the signal difference, but we don't get any usable signal at all. So indeed, the other option would be to go as fast as possible, take the shortest possible echo time, and then we measure the signal difference. And in this case, we don't get the T2 contrast. If we take a very short echo time, we don't get differences in the speed of T2 relaxation. And like it's shown here on the slide, we do get a signal difference due to the T1 relaxation. Now, if we summarize that whole process, the previous slide, into sort of a table, you would get something like this. And the good news is that if you didn't really understand much of the previous slide, you can just learn this table by heart. And also, in practice, you would also have different kind of radiologists. Some really do understand the previous slide and they can think about optimizing sequences and what you can do and stuff. And other radiologists, just look at the images and know all the procedures. Doesn't make them better or less good. Radiologists, it's just a different way of thinking. But you would have to remember this diagram, this table, to understand actually what you're looking at. Because the echo time, the repetition time, they will be denoted on the screen alongside with the images, the annotation. So it says here, like if I have a very short echo time, by short I mean much shorter than the T2 relaxation constant of the tissue, meaning we're sort of really upfront on the beginning of the curve, where the signals don't split up yet. That is a short echo time. And then if we have a short echo time, we are in a situation where the repetition time actually determines the contrast. Because a short echo time means we don't have T2 contrast. Now what do we get? Well, if we have a short repetition time, short meaning sort of roughly order of magnitude of T1 of tissue, then we have the recovery curves, the longitudinal recovery curves, being cut off at the point where the decay curves split up. And at that point in time, if we use the next RF pulse, we get a T1 image. We wait really long until we give the next repetition, the next RF pulse. Then we don't get G1 weighted image, but we do get sort of the default contrast, which is proton density. We do wait very long until we give the next excitation pulse. All the longitudinal magnetization has recovered. And at the point in time when we do the excitation, we get sort of don't see any difference in the longitudinal. So we get the proton density there. Now, if we have a very long repetition time, much longer than T1, we can create a T2-weighted image if we take a longer echo time. We take the echo time order of magnitude as the T2 of the tissue. We have the curves again, transverse magnetization curve split up, and then we get signal difference between gray matter and the white matter again. In terms of T2. And then here we have this sort of box mixed contrast. Usually would like to stay out of that area because we have that T1 contrast and the T2 contrast mixed in at the same time. We tend to sort of cancel out that both contrasts because they are opposite appearance in the image. And that means if we have this kind of contrast, we might miss pathology, etc. So it's a kind of corner of the table where we film it. Okay, and now we have this formula. It's a mathematical description of basically it's a multiplication of the formulas we saw earlier on. One relaxation. Let's do relaxation there. Any questions so far? None. It's just, yeah, if you like formulas, my day off. If you don't like formulas, sure. So you remember? The principles is this table. This kind of, you can sort of execute better like the formulas. If you remember the formula, you can sort of rebuild the table from the formula for that. All right. I would say that the T2-weighted image is kind of the workhorse for the radiologists because many types of pathology are shown nicely on T2-weighted images. For example, edema shows contrast, tumors shows up nicely show contrast, MS lesions show contrast. So if you see something shown having abnormal signal difference on a T2-weighted image, it's likely to be pathology. The other way around, many pathologies are detectable with T2-weighted imaging. At T1-weighted imaging is also used a lot because it does show the anatomy very nicely and it's very efficient. Within a reasonable scan time, you get really nice detailed images. And in general, it is used as an additional indicator for pathology. And the way that radiologists often work is that look at the T2-weighted images, they get an idea of what pathology might be. Then they seek confirmation on other tissue contrasts, other image contrasts. So they expect to see a certain appearance of that pathology on a T1-weighted image. And if that is what they get to see, sort of confirms their hypothesis for the pathology. And the same sort of holds for the proton density weighted image. Basically, that's only used nowadays for MS lesions. But in general, I could say it's additional information. So basically, what I've shown so far, I would regard as the really basics of MR imaging, MR image contrast. Now I have a couple more slides showing you some tricks that are being used in clinical practice a lot, and that we also are going to use in the computer simulations tomorrow, so he will play along with that as well. We're going to now talk about magnetization preparation process. And the concept there is that we do a manipulation of the state of the spins, the compass needles. We're going to manipulate the compass needles before we do the RF excitation pulse. It's shown on this block. So do something, then we do what here's the green block on the right. Imaging sequence is a repetitive excitation pulse and getting that signal, as we've seen before. And what we can do here on the block on the left, magnetization preparation, is like something like saturation pulses, inversion pulse, fat suppression pulse. I will talk about the inversion pulse as an example. So the inversion pulse is 180 degrees excitation pulse, you could say. So we do a stronger RF wave, which rotates the spins all the way to the opposite direction. So it's a 180 degrees. Sort of the compass needles will be rotated all the way against the field. As shown here on the bottom, this is the equilibrium state. Right after the inversion pulse, the longitudinal component is vertically downwards. So what happens after we use this inversion pulse? What kind of relaxation process would be of interest, would you say? We manipulated the longitudinal component. So the relaxation rate of the longitudinal magnetization is T1 or T2? It's T1 relaxation. So after the inversion pulse, you will get one relaxation curves. The only difference with what we saw previously is that now starting point of the relaxation curve is -1 because it's inverted. It's all the way against the field. But the shape of the curve, but the rate of relaxation is identical and is determined by the T1 of the tissue. So here I show the three tags, white matter brain and CSF. Obviously, CSF has the longest T1 reaction rate, the slowest. Let's go fast. Now I introduce a new knob, a new parameter that we can set on the MR scanner, and it's called inversion time. It's defined by the time I waiting time between 180 degrees inversion pulse and the moment I do my first excitation pulse of the imaging sequence. And that waiting time determines kind of which point in this T1 recovery curves I'm going to get my signal. So in this case, I have a lot of signal difference if I do 180 degrees excitation pulse at point in time. All the different tissues have a different longitudinal magnetization. That by the first excitation pulse, I'm going to rotate transversely and measure that signal. So they will all give different gray values. And in this case, obviously, I get a T1 weighted image. If I do this repetitive and wait for the signal to recover all the way to equilibrium state and do it again, my scan time will be really, really long. So what I usually do is, at this point in time, I do a sort of repetitive, really fast imaging sequence, which I'm not going to explain details of, to scan a lot of information to build my image. But the contrast is in this case generated by the inversion pulse and the waiting time from the inversion pulse. I get a T1 weighted image. Here's another example, which is used very often in clinical practice, and it's called pure fluid attenuated inversion recovery, or FLAIR. Seen a lot of those images in my lecture. And what it does is it deliberately waits until the signal of CSF has gone to zero. So the longitudinal component, the factor, so it comes to equilibrium with the T1 relaxation rate. And at this point in time, crosses zero. So the length of my longitudinal vector is zero. If I rotate a vector of length 0 in the transverse plane, it still has length 0. Meaning I will not get signal from the CSF. I'll do it this way. If I look at the signal or the longitudinal magnetization of gray matter and white matter, I have almost recovered to the equilibrium state. The signal difference is not big, meaning I don't get signal from CSF, and roughly get same kind of signal from white matter gray matter. So if I do the excitation pills, 93 excitation pills at this point in time, I can add T2 weighted contrast because I don't have a lot of T1 weighted contrast between gray matter and white matter. So if I choose my echo time, roughly the same order of magnitude as the T2 tissue, gray matter, white matter, I will get any T2 weighted image. So I will get a T2 weighted image, but not get a exponent. And the is suppressed. This slide shows clearly shows again the news of that trick. On the left hand side, you see the T2 weighted image. This image is from a patient with MS, and the MS lesions show up with on a T2 weighted image show up with a bit of a brighter signal. In early MS, the lesions tend to start very close to ventricles, so very close to the highest bright signal to see that. So here at the edges of the ventricle, see the extensions, so it's a vaguely bright signal, but it's really hard to detect them because they are so close to the bright signal of the CSF. So is it signal from CSF or not? Is it a lesion? The thing holds here on the backside of the brain. Here you also see an extension of the signal, but is that XPMS? Now, if you suppress the bright signal from the CSF, you get the FLAIR image shown here on the right-hand side. Now we don't get the CSF, it's very dark, but we do get the signal from the lesion because it is a T2 weighted signal. And the CSF is suppressed because the CSF has a very long T1 and has we chose the waiting time, infusion time, really long to, have the signal from CSF go right through zero. And then we do get the signal in the lesion by a T2 weighting due to the longer echo time. That's called FLAIR, fixed on two-weighted imaging, suppression of the CSF. You have some other examples of signal in MS, different types of contrast. Here we have the FLAIR image. You see the lesions. You can also vaguely see the lesions in the cortex, gray matter. Difficult to see them. And that's why someone came up with double inversion recovery, two inversion pulses. They are timed such that both signals from CSF and from white matter are suppressed. And you only get the signal from gray matter, and you can really nicely see lesions in gray matter. And here we have the regular T2 weighted image that also shows the lesions. It's sort of mixed up with the signal, high-right signal from the CSF. Then here on the right-hand bottom side, you have the regular T1 weighted image that shows the lesions gray matter. Really difficult to see because they are dark. The T1 images usually have the opposite contrast of the T2. Now the lesions are shown in darker signal, which means they're difficult to read.
So the contrast agents that we use for MR imaging consist of paramagnetic or ferromagnetic agents, and they sort of interact with the compass needles, with the protons. And what they do is the interaction results in a reduction of the, where's my pointer? A reduction of the T1 and T2 relaxation times of protons existing in water. So the contrast agent itself does not produce an MR signal, but it influences the relaxation rates of the protons. And that is in contrast with, for example, CT, where you inject iodine, and the iodine actually absorbs a lot of the X-rays. So that actually does produce a contrast itself. But here we talk about, again, influencing of T2 and T1 of relaxation rates of water. That results in a shortening of T1, and that means there's an increase of MR signal on T1 weighted images, because by now you should know that a short T1 results in a bright signal on a T1 weighted image. So if we inject a contrast agent, it will produce a bright signal on a T1 weighted image. Now in principle, the paramagnetic, ferromagnetic agents could be different kind of ions. For example, manganese or iron particles. But the most widely used contrast agent is gadolinium. Now, gadolinium itself is a bit toxic, but I'll show you on the next slide how it's used. This shows you an example of the contrast agent before the use of contrast agent. So this is a regular T1 weighted image, and then after applying the contrast agent and let it sort of dilute into the pathology, into the tissues, we get a signal enhancement at the location where the contrast agent accumulates. Now, in the normal brain, the contrast agent doesn't go into the brain tissue; it stays in the vessels because it can't pass the blood-brain barrier, the intact blood-brain barrier. But in this case, we have tumor growth, and then there's leakage of the contrast agent because there's newly growing vessels. The blood-brain barrier is sort of leaky in those areas, and we get the contrast agent to leak out of the vessels into the tissue. That's why it shows up bright. And in this case, it's an example of two brain metastases of a patient that has lung cancer. It's easy to detect with the contrast enhanced imaging. Now, so in the previous example we saw there's T1 shortening, but there's also shortening of the T2 relaxation rate, and that means we get signal enhancement on T1 weighted images, but if the concentration is high, we get shortening of the T2, and we get a signal reduction on T2 weighted images. And there's also a use for that. But first we look at how the contrast agent is built. And the gadolinium is, as I said, is toxic.
So what the manufacturers of the contrast agent do is they build the gadolinium ion into a larger molecule. So they have a shell that sort of renders the gadolinium iodine to not to interact with the tissue at all, and that's called gadolinium chelate. And the formula, the exact chemical substance of the shell is different between the manufacturers. So you can have different contrast agents with different names. The difference is always in the sort of shell surrounding the gadolinium, but the principle and the of the iodine is the same. So it works by using intravenous injection. The contrast agent is an extracellular agent, so it stays out of the intact cells. No passage of the intact blood-brain barrier, and where the blood-brain barrier is damaged, basically the tissue enhances, being very sensitive to leaky vessels with angiogenesis tumors. The contrast agent has about 90 minutes half-life, and it predominantly is cleared by the kidneys. And the applications include angiography, tumors showing up lesions. As I showed before, there's a scan before and after administration of the contrast agent, and then you can easily detect the areas in the image where the tissue is higher on the post-contrast image. And you can also do perfusing scanning, which is a dynamic scan during the injection of the contrast agent, which I have some examples in the presentation on Wednesday, because I think for now we have covered all the topics we need for the next lecture and the computer practicals. And I think you are also pretty saturated with all this information. So the reason is also why we do the computer practical. Tomorrow you will play with the simulator, play with the sort of MR scanner, and use all the information that we've shown today. And I think the table sort of in my presentation showing the relation between the echo times and the different contrast weightings, T1, T2 weighted images. That slide is actually key to working with the computer simulations tomorrow.